Talk about acid base. So I realized I kind of put myself in a box when I told Felipe I was going to do acid base. Because he's like, you have 20 minutes to do acid base. And I said, well, I can't do acid base in 20 minutes. So he gave me 40 minutes. And then I realized, well, I can't really do acid base in 40 minutes. And no one wants to listen to acid base for 40 minutes. So now I'm kind of stuck. But we're going to do it. I actually love acid base. And I have a lot of fun with it. And hopefully you will too. We talked about my disclosures already. Financially, I have none. Intellectually, I write for a blog called EM Nerd. I think the big one for this talk is I'm an EM physician at heart, which means I have the attention span of a goldfish. And so what we're going to try to do today with acid base is probably entirely different than what you've done before, because I want you to shift your perspective on what acid base is. And there is a huge grudge match in acid-base physiology. There's various ways you look at it, from Stewart approach to Henderson-Hasselbalch approach to base excess approach. And in the end, they really are kind of, in the end, they kind of are looking at the same thing from different perspectives. And I find a lot of times what happens with acid-base is something like this, where you're ending up asking to do a lot of math, and in the end, you come up with an answer, but it's so far away from what actually is clinically happening that you don't really know what to do with it, right? And so the point of acid base is to tell you something that's happening clinically, and you actually get to use it to make an actual difference. So this is sort of what you end up doing. So this is like New England Journal, Henderson-Hasselbalch acid-base formulation, right? And you can see how big it is. We don't have to run through it all because that's not exactly what we're not going to do today. But anything it ends with calcium delta-delta and urinary anion gaps usually leave me confused and tired. So we're going to do something far simpler than this. And Stewart really isn't much better. I'm a Stewart approach person, and I like quantitative acid base. But if I have to calculate 5 different formulas on shift, I get a little bit tired for every patient. So I kind of devised this kind of bastardized approach that's fairly simple, that you have to do very little math. And it allows you to do acid base on most patients without even having a blood gas, for the most part. You know, it's shocking that we don't get blood gases. So it looks more like something like this, right? You have a simple answer and you get right through it. So there's a couple ground rules that you have to do if you're gonna actually engage in this kind of bastardized acid base approach that I'm using. And the first one is you have to stop caring about the actual number, the pH. Because I'm going to suggest to you the actual pH probably matters a lot less than what's causing the acidosis in the first place, right? And you know, we have a lot of theories that when you become acidotic, your heart stops working, and pressure stops working, and inotropes stop working, and you guys know what that data is based on? So it's based on these guys. They take bunny rabbit hearts, take them out of the body, and stick them in either a normal pH solution or an acidotic solution, see how it contracts and see how it responds to inotropes. Now, I'm not sure how pickled rabbit hearts corresponds to humans, but I don't think very well, right? And we can actually look at some data suggesting it might not mean that just acidosis in and of itself makes much of a difference. So Olympic rowers measured their pH right after they did a race. You know what it is? 16, right? What's the lactate? 24, right? You know what their potassium was? It was something like 9, right? Their hearts were beating just fine. They didn't fall over. They did great, right? Has anyone heard the Fruman study, apneic oxygenation in man? So this is a fantastic study that no IRB would pass anymore, but essentially they took military recruits that were going in for elective surgery and they intubated them and paralyzed them, but instead of ventilating them, they ran oxygen tubing down the ET tube and passively oxygenated them. And they did it for over an hour on some cases, right? And their oxygen stayed completely normal. Guess what their pHs were? Oh, I don't know what that's in, sorry. Well, more suspense. Here you go. So they had PCO2s up to 250. There's their pH, right? And they actually looked at their heart. And what was their heart doing? It was completely normal. They had no problems. They woke up and they functioned as well as we can tell they did with no deleterious effects from this, right? Okay. And we've all seen DKAers down to 6, 7, 6, 8, put the probe on them, and their heart is kicking fine, and they have no hemodynamic compromises. And yet, if you look at a septic patient at 7.2, they're dying, right? And salicylate overdose, 7.35 is essentially dead, right? So the point of this is it's not the pH that matters, it's what's causing the pH that matters. And your acid-base approach shouldn't be trying to figure out what the numbers are, but trying to find the underlying cause so you can correct that. Okay, so ground rule number 2 is the hydrogen and bicarb are dependent variables, and they're actually dependent on variables and dependent on other independent variables. So your body will make as much or as little from water and CO2, right? And so the actual dependent variables are CO2, weak acids, stuff like albumin and phosphate in your blood, and strong ions like sodium chloride, lactate, so on and so forth. And so this is what causes acid base, and this is the stuff you want to figure out what's going on, and we'll kind of talk a little bit more about that in a sec. The third one is, a lot of us are approached as kind of accusatory status of acid base, right? So you make judgments on it. So, you know, the patient has a chronic respiratory acidosis with compensation, or the patient has a metabolic acidosis and is compensating or not compensating respiratory-wise. And instead of saying that, just say what's actually happening, right? So, you know, classically, if you had someone with DKA, and they had a metabolic acidosis and anion gap acidosis, but their PCO2 was 40. You would say, well, they have a respiratory acidosis because they're not compensating right. But technically, their PCO2 is 40. They don't have a respiratory acidosis. You have to make a clinical choice whether they're compensating right or not, right? So it makes it simpler. Instead of you trying to figure out through math to figure out if they're compensating or not compensating, you just look at the numbers, say what they are, and then make a clinical decision based on the patient themselves. All right, so we're going to jump into this. Unfortunately, because I only have 40 minutes, I'm going to spend one slide on respiratory acid base, which some people might find is a good thing. But respiratory acid base, from this standpoint, is actually pretty simple. Respiratory CO2 is not a weak acid itself, but it turns into a weak acid. And so you have increased levels of CO2, you have an acidosis. You have decreased levels of CO2, you have an alkalosis, right? I'll tell you, there's no actual data showing that your PCO2 correlates with whether you have to intubate a patient, and a lot of that is based on clinical status of all. So that's all we're going to do for respiratory. If people like this, we can come back next year and do a real talk on respiratory acidosis. We're going to spend the rest of the time on metabolic acidosis. And when we're talking about metabolic acidosis, it's the law of electrochemical neutrality, meaning all our cations have to equal our anions, right? And so largest cation in our blood is sodium, right? So you got a big block of sodium there, and what else do you have? Calcium, potassium, magnesium, and then you have a tiny bit of hydrogen up there at the top, right? And so your cations have to equal your anions, right? And to make this simple, because like I said, we say that it's just sodium, because the other ones don't have a clinical status. Most of the time, you can just calculate your sodium as your cations and kind of ignore the rest. And this has to equal your anions, right? Largest anion is chloride, and then bicarb. And then that last one, what's in the green box? Albumin, right? But this is what we classically call our gap, right? And the gap is not a literal gap, it's just filled with stuff that we used to never measure, mostly measure now. So it's albumin, phosphates, and sulfates, and so forth, right? So this is everything about acid base, right here. This is all you have to know, is this kind of schema. Because the only way that you become acidotic from a metabolic perspective is one of two ways. Your chloride increases and your bicarb decreases. Or your gap increases and your bicarb decreases. That's it. That's all there is to it, right? So the only way to become alkalotic is your chloride decreases and your bicarb increases in relation. Or your gap decreases and your bicarb increases. So you can quantify all acid-base status by just looking at that relationship on every single patient. And you can do that without a blood gas. You just have chemistry, and you can figure all that out, right? And since you don't care about the actual pH, you care about what's going on, from a basic chemistry, you can get most of your answers. And we'll kind of run through how you do that from here on. All right, so like I said, you need a way to quantify, You need a way to quantify how much chloride's in your system in relation to your sodium, and you need a way to quantify what the gap is in relation to your sodium. Remember, it's always in relation to your sodium, right? Because the cations and the anions have to equal, right? So a simple way to quantify the difference between your sodium and your chloride is sodium minus chloride, which is known as our SID, right? And the simple way to quantify the gap, which we already do, sodium minus chloride plus bicarb, which is known as our gap. You do these independently, they're telling you different things. So the SID is telling you how much chloride's in your system in relation to your sodium, and the gap is telling you how many unmeasured anions are in your system in relation to your sodium, right? That's all you have to do. And that'll tell you everything you need to know from a metabolic profile of acid base. All right, lecture's over. Thanks for now. Okay, we'll go through it. All right, so a SID, a normal SID, if your sodium's around 140 normally and your chloride's about 102, a normal SID is somewhere around 38 plus or minus 2. So we say SID's over 40 is elevated, right? So what does a SID over 40 tell you? Just have to think about it for 1 second. Means there's more sodium in the system in relation to our chloride, right? So there's decreased chloride, increased bicarb, you have a metabolic alkalosis. Make sense? Yeah. Okay, so stuff that causes classically vomiting. Why does vomiting cause a metabolic alkalosis? Yeah, so Henderson-Hasselbalch will tell you the loss of hydrogen atoms if you're vomiting. You can't just vomit hydrogen atoms, there has to be an anion with it and it's chloride, right? So you're vomiting hydrogen atoms and chloride until your chloride goes down, your sodium stays the same, you expand your SID and you get an alkalosis. Dehydration, why does dehydration cause it? So what does the kidney do when you're dehydrated? It reabsorbs sodium, right? And it reabsorbs sodium, some of that sodium is in the form of sodium bicarb, right? So you're reabsorbing sodium, your chloride stays the same, and you get a metabolic alkalosis. Chronic respiratory acidosis. Why does that cause a metabolic alkalosis? You're taught that your kidney's holding onto bicarb. What is it really holding on to? Sodium bicarb, right? It's holding to sodium bicarb. So you're holding on to sodium bicarb, your chloride's staying the same, your sodium's going up, and you're expanding your SID. Bicarbonate infusion, we'll get to that one later, that's the most fun. Okay, so SID's less than 36. That's telling you there's more chloride in your system in relation to sodium. Right, so you have a hyperchloremic or SID acidosis. What are the things that classically cause this? Diarrhea. Why does diarrhea cause acidosis? Classically, you learn that you're spilling bicarb in your feces or in your diarrhea. What are you really spilling? Sodium bicarb, right? So you're spilling sodium bicarb, so your sodium's going down, your chloride's staying the same, your SID gets less, you get an acidosis. AKI. Why does AKI do this? So your kidney will try to reabsorb sodium and expel chloride, and when you start having actual extrinsic dysfunction, you do that less often, right? So you actually spill sodium bicarb and reabsorb chloride in exchange for it, right? So your chloride gets higher and your sodium stays the same, you get a SID acidosis. RTA. So RTA is very complicated, far more complicated than I actually understand, but the simple thing is they're all the same in the end. All of them reabsorb chloride and spill sodium bicarb, right? And a saline infusion, that's the most interesting, right? So why does a saline infusion cause hyperchloremic acidosis? Before I get there, sorry. So what are all these acidoses? What do you traditionally know these as? Non-anion gap acidoses, right? And it's funny, like when you learn non-anion, they don't tell you they're all hypochloremic. Every single non-anion gap acidosis is the same anion. It's all a hyperchloremic acidosis, which makes it much simpler when you think about it, right? Okay, so why does normal saline cause a hyperchloremic, a SID, or a non-anion gap acidosis? So if you look at it, how much sodium is in there? 154 millimoles. How much chloride? 154. What's the SID of normal saline? 0, right? So you got a SID of 0. What's the SID of your body? 38 or something, right? So you're giving a chloride-rich solution. So the more you give, the more your actual blood starts to look like the solution you're giving, and so your SID drops because your chloride goes up, right? So you're decreasing your SID because of the fluid you give. So to get it even cooler, what about lactated ringers? Why is lactated ringers a balanced solution? It's got a lot of stuff in it, but what does it have in it other than chloride, right? What's the anion it's replacing chloride with? So some buffer base. The answer is in the name. Lactate, right? So you're giving them sodium lactate, right? But lactate's a strong anion, right? That's another anion that causes the acidosis. So why don't you get the same acidosis you get from normal saline that you get from lactated ringers? Goes to your liver. It turns into pyruvate and goes into the Krebs cycle. So you're giving free sodium, which is really cool, right? So you're giving free sodium, your SID expands. What about plasma? You guys have plasma? Yeah, what about plasma? Jeez, I'm sorry.
You could turn your Wi-Fi off.
Is that what I can do? Sorry, guys. So what about plasma? So what's the buffer base in plasma? It's sodium acetate, right? And so again, sorry, acetone, excuse me. It's acetate, that's wrong. It's sodium acetate, I'm sorry. So it's sodium acetate, and what happens to the acetate? Because acetate itself is a strong anion, right? Same thing, it goes to the liver, gets turned into acetyl-CoA, and goes into the Krebs cycle, right? And so again, you're giving free sodium. So here's the coolest one. What about when you give people bicarb? What are you actually giving them when you give them bicarb? It's not just bicarb. Sodium bicarb, right? And so if you actually put sodium bicarb in a sealed container and don't let it off gas, what does it do to the pH? No, right? So how does this cause you to become more alkalotic? Turns into CO2, goes to the lungs, and you're giving free sodium, right? And so the alkalizing or acidotic effects of any one solution that you're giving someone is dependent on the SID of the solution itself compared to the bicarb of the patient that you're giving it to, right? So the SID of normal saline is 0, and a normal bicarb on any one patient is typically 24. So it's an acidotic solution. What's the SID of lactated ringer? It's about 24, right? So it's a pretty balanced solution. It doesn't do much to your pH. If you have a normal bicarb to start, if you have a chronic retainer and you have a bicarb of 36, lactated ringer has now become an acidotic solution because the SID of the solution is less than the bicarb of the patient. Plasmally, what's the SID of plasma? It's about 50, right? So it's a reasonably alkalotic solution in most people. And then the SID of a bicarb infusion is whatever you make it, right? So if you put 3 amps in G5W, it's somewhere around 150, right? So that's why it's such an alkalizing solution. Make sense so far? Right? So the argument here is, there's a lot of people that are pro-balanced solutions, say normal saline is evil, but then are anti-bicarb drips, which is kind of crazy. It's the same thing, right? All you're doing here is messing with your SID and changing your SID balance to affect acid-base status. We have no idea what the clinical actual consequences are. If you look at most of the data on normal saline versus balanced solutions, I think we're still up in the air. I think when Plus and Basic come out, which will be really well done randomized controlled trials, we'll probably have a little better answer. But we really don't know if messing with your SID simply to change your pH or your acid-base status has any clinical effect. But that's what you're doing when you're playing with all this stuff. All right, so we'll move on to anion gap. So you can actually have a low anion gap, right? Which should cause an alkalosis. And we don't often talk about this, but it happens and we see it in the ICU a lot, right? So in the ICU, someone gets admitted and all of a sudden over time you see their bicarb going up and up and up and up. And sometimes you think they're dehydrated or over-diuresed or so forth. But if you actually calculate their SID is normal, and you say, well, wait a minute, why is their bicarb 30 or 32? And then you look at their gap and it's 2. So what happened? They all fell their albumin, right? So their albumin, over time, as you don't have adequate nutrition, you start losing it, right? So their albumin goes to 1.8 or something of sorts, and they started getting an anion gap alkalosis, which sounds like a strange thing, but it really happened. The important thing to know about this is where you can miss anion gap acidosis. If someone should have an anion gap of 4 because their albumin is like 2, and they have an anion gap of 8, there's 6 extra anions in there that you have to go find. Now Henderson-Hasselbalch has you do like a calculation for this. So they basically will give your gap. So say like you calculate a gap of 8, and then they say your albumin is 2, so you multiply your gap by 2.25 to get this kind of artificially elevated gap, which seems silly. Their gap's 8, that's what it is. And the numbers, to artificially elevate it just to get a number seems weird. What I would encourage you to do is figure out what the real gap should be. So if their albumin's 2, you can. There's a couple different formulas. A simple way I usually do is multiply it by 3. So if their albumin's 2, their gap should be 6. So anything above that, there's another anion in there that you have to go find. Does that make sense? All right. So this is probably the most important, right? Anion gaps greater than 15 is an anion gap acidosis. And why are anion gap acidosis far more serious than non-anion gap, also known as SID, also known as hypochloremic acidosis?
Because they might have specific treatment.
Yeah, there's stuff in there that actually kills you. Like people who have chronically have SID acidosis all the time and they do fine, right? They walk around with it and it's not a functional problem. Sometimes they get some, calcium leaking of their bones and so forth, but there's not an acute clinical problem that we're dealing with most SID acidoses, right? But these have stuff that'll really kill you, right? So this is why it's important to actually figure out what's causing the acidosis and not just calculate a number, give some bicarb or give some balanced solution and think we're gonna make them better, right? And so this is our classic mnemonic to figure out what things fill your anion gap, mud piles, right? And so the trick here is not to actually remember what each one stands for, but it's to know the anion that's filling the gap so you can actually figure out stuff, right? So M is for methanol, right? And what fills the gap in methanol? What's the anion that's causing the acidosis? It's formate, right? So methanol gets broken down through alcohol dehydrogenase into formate. Methanol itself doesn't cause an acidosis, but when it turns into formate, you get one, right? Formate is a neurotoxin and cardiotoxin. That's why they tend to go blind and die on you. U is for what? Uremia. What's the anion? So it's not uric acid. It's actually phosphates and sulfates, right? This is why when you have people with chronic renal insufficiency, you give them phosphate buffers to try to buffer out that phosphate, right? And so we use the BUN as a surrogate for what's actually filling the gap. But this one's a little tricky because you can't actually quantify just because your BUN is 90 doesn't mean the elevated anion gap to 25 is fully filled by phosphates and sulfates. There is some data saying you should take your phosphate, multiply it by 0.5, and that'll give you how much it filled, though you actually go back in literature, you can't find any actual sources of where that came from. And it doesn't always work out. There was also something saying that you should never apply an anion gap greater than 25 to purely uremic acidosis. Again, that was just someone who said that in the New England Journal in the 1970s, and we kind of stuck with it. But you always want to be worried when you have an anion gap of 32 and you're applying it to it's completely uremic acidosis, right? I tend to keep looking for other things. So what's D? AKA in starvation ketoacidosis, and the anion is ketones, right? What are our standard ketones?
Beta-hydroxybutyrate.
And beta-hydroxybutyrate and acetoacetate, right? And they exist in equilibrium depending on the redox state of the patient. And beta-hydroxybutyrate spontaneously decarboxylates to acetone, right? And this is not just to sound smart. This is actually has some clinical practice. So your urine ketones is measured what? Acetoacetate, right? And so there's certain states in ketoacidosis that exist entirely in the form of beta-hydroxybutyrate dependent on the redox state of the patient. So example, alcohol ketoacidosis. You drink a lot of alcohol, it's broken down by alcohol dehydrogenase into acetate, right? That produces more NADH, which shifts you from making a whole lot less acetoacetate and a whole lot more beta-hydroxybutyrate. So patients come in deep in alcohol ketoacidosis and their urine is negative for ketones and they have a gap of like 45 and you're freaking out that they have methanol or ethylene glycol toxicity and you give them a little sugar water and they get better. But just knowing this foil kind of solved the whole thing of giving someone a whole bunch of fomepizole when they don't need it. All right, P. P is dependent on your generation, right? So you can tell how old a doctor is depending on what they call P, right? So originally it was paraaldehyde. Who here's used paraaldehyde? Right? So paraaldehyde used it for alcohol withdrawal. It apparently has a sulfur smell to it from what I've been told. It causes lactic acidosis. I use fenformin as a marker. And this might be my ED roots. Probably a lot of ICU docs use propofol as this. But fenformin was an old version of metformin that was taken off the market because it caused a massive acidosis. What kind of acidosis? Lactate, right? So it's a lactic acidosis. Usually you have a pretty bad kidney injury with this. You guys know what I is? Ionation iron, right? So all your hydrozydes cause that. It's not only iso-INH, right? So rocket fuel or gyrometrum mushrooms all have hydrozydes in them. They'll all cause the same thing. What kind of acidosis does it cause? This is important because, like, so you get this anion gap and you don't know what it is, and the person happens to be on INH, and you think it's INH toxicity, and what's the antidote for INH toxicity? Vitamin B6. How much vitamin B6 do you give them? It's like 5 grams. And what does it come in? It's 100 milligram glass bottles that you have to break open, so you have to crack open 50 bottles, which is not fun. So it's nice to know if they actually have this or have a pretty good chance of having this before you break up all the bottles. So what does INH toxicity look like? Status, right? So it's status that's refractory to benzos, right? So if it's status refractory to benzos, what's the anion gap? What kind of acidosis does seizures cause? Lactate, right? So it's a lactic acidosis, and if they're not seizing, it's not INH toxicity. So you can save all the vitamin B6 for some patient who's vitamin deficient in the ICU. What about iron? Iron's a mitochondrial inhibitor, so it's a lactic acidosis. They're usually vomiting a lot of blood. They're usually sick as crap. And most of the time you can catch it on an X-ray of the iron. There's some idea that if you have iron levels over 300, it's diagnostic, but you can have patients with lower iron levels if they've been chronically taking this, or if they presented late that are still pretty sick from iron toxicity. L. So this is the only one where the anion is on this side of the table. Right? Every other one, the anion was the other side of the table. And this is kind of to remind you a couple things. So when you say lactate, what do we traditionally think of? Sepsis, right? Because we've all been taught that we have to get lactates in every septic patient. And this is to remind you that if you see a patient, more so in the emergency department than the ICU, but a person presents in the emergency department with a lactate of 10, may very well sepsis, but there's a whole bunch of other stuff that will truly cause tissue hypoxia that you have to go work up, right? And the most common ones that we see in the ED, CO, cyanide, and some form of gut ischemia or total body ischemia, right? So it's just to remind you that not all lactates are sepsis, and elevated lactates that are quite high, you should go looking for other sources of the cause. What's E? E is ethylene glycol, right? And what's the anion in ethylene glycol? So it's oxalate and glycolate, right? So oxalate are the ones that bind with your calcium, causing calcium oxalate crystals. That's what deposit in your kidneys and deposit in your brain, cause you have seizures, deposit in your heart, and you tend to die with it, right? And S is salicylates, and what's the anion in salicylates? It's like a mixed ketone lactic acidosis, right? So now we've run through this whole thing, right? You got your whole list, you can pretty figure out. And the whole point is now, what lab tests do I have to order to figure out what's filling my gap? Because that's what I really want to know, right? I want to know what's causing my acidosis, right? So you can order a BUN, a lactate, ketones, and an aspirin level. And if they're all negative, what have I ruled out? Everything but methanol and ethylene glycol, right? Because what's the traditional way we try to rule out methanol and ethylene glycol? You calculate a what? An osmond gap, right? And how good is an osmond gap? It's terrible, right? So the sensitivity and specificity of the osmond gap are just clinically unusable, right? So you can fit a lethal level of both these drugs in a normal osmond gap, right? And if you just walked around the ICU and measured a whole bunch of osmond gaps on patients that don't have these toxicities, they'd be elevated. So it's not very useful. If you get an osmond gap around 70 or 80, there's not much else it could be other than toxic alcohol. But I would argue if you have done this and you have no other source of anions, you should probably treat. The treatment is fomepizole and plus minus dialysis, depending on the situation. The one foil here is what we talked about, alcoholic ketoacidosis. Right? Because if you don't have a beta hydroxybutyrate serum level, which some hospitals don't, I actually don't in my hospital, you get this whopping anion gap that you can't find a source for, right? And the alcoholic who has AKA is also the type of patient that you might worry about some kind of alcoholic ketoacidosis or some kind of toxic alcohol ingestion. What I do is typically in those patients, I give them a bunch of sugar water, and if they get better, it's obviously not a toxic alcohol. If they don't get better, then I start to go down the pathway of treating them for toxic alcohol. All right, so that's it. That's all of acid-base, made really simple. You can dive really deep into this stuff if you want, and it's fascinating. But this allows you to have a protocol or a system where you can look at any chemistry and quickly calculate their acid-base status, and then actually decide whether you're worried about it or not, right? So I put it in a little kind of diagram here. Hopefully it looks much simpler than all the other ones that we've kind of done. So it's pretty simple. Their pH is low. I would argue I don't often actually know what their pH is because I don't really care about the number. But if you want to, you can actually see if they're acidemic or alkalemic, right, by their actual pH. Their PCO2, again, instead of trying to figure out if they're appropriately compensating, chronic, not chronic, I just call it by the number it is and make the clinical call on the patient themselves. So if their PCO is normal, if it's elevated, they have a hypercarbic acidosis, and if it's low, they have a hypocarbic alkalosis. So, right, up, down, just call it. And then all you're doing is calculating your SID. These two I do on everybody. Those two I mostly don't do unless I have a blood gas that someone happened to order. Remember, a low SID tells you that there's more chloride in the system in relation to your soda, right? A high SID tells you that there's not enough chloride in the system, and that's an alkalosis. Incidentally, what is this actually doing? If you calculate a SID on every patient, what do you never have to calculate? The delta-delta, right? Because the delta-delta is trying to figure out what other acid-base status is going on with your patient. It's essentially calculating your SID. I think calculating a SID makes much more sense than trying to figure out what your delta-delta is. So I haven't calculated delta-delta in years. I just calculate my SID, and it tells me what other acid-base status is, right? And every time you calculate a SID, it's a hyperchloremic status, right? That's telling you about what's going on with your chloride, right? And finally, you calculate your gap, and this is probably the most important thing you have here. And I would suggest when you do calculate your gap, eyeball your albumin, make sure your gap should be normal at baseline. Because if you have a gap of 12, but your albumin's only 2, you should be concerned there's another anion in there that you should go look for. All right, so that's it. That's all of acid base. Hopefully I didn't bore you guys, and hopefully we had fun. Any questions?
Metformin overdose will also give you a very high lactate, right?
That's exactly what it does, yeah.
Yeah, so would that also come into that?
Yeah, so I cheated a little. I called metformin fenformin.
Oh.
Because fenformin was the old version of metformin that was taken off the market.
Okay.
Yeah, it'll cause a pretty whopping lactate acidosis. You know, if you actually look at the data, it's interesting. Like if you look at the Cochrane group, if you actually read their analysis, they say they have no evidence anywhere that a metformin acidosis actually exists, that there's any evidence that's a real thing. But if you talk to any toxicologist in the whole world, they're saying that's crazy, we see it all the time. And it's probably because the patients that were actually enrolled in the trials on metformin were never at risk for metformin acidosis in the first place. So that's probably what we're seeing. But most toxicologists believe it's a real thing, and you can measure whopping metformin levels in patients who have whopping acidosis, and when you dialyze out their metformin, they get better. But that's about all the evidence we have.
So with toxic alcohols, does that occur, like that's
Yeah.
the metabolic component shows up later?
Yeah.
So how long do you wait till you test the numbers on the?
So it's a really good question. So basically what happens if you ingest, let's say you have someone ingest methanol in the parking lot, right? And so when they ingest the methanol, it takes about 15 to 20 minutes to be absorbed into the bloodstream. You have an electrochemically inactive substance in your blood, right? Something like methanol, right? And so your anion gap is normal, right? And so your anion gap is low. And over time, as it gets broken down into formate, it goes up, right? But at the same time, the methanol is dropping, right? And so the interesting part, why, because formate's also a molecule, right? Your Osm gap is essentially trying to quantify how many molecules you have in your blood. But formate's a molecule, so why is your Osm gap dropping as you convert methanol to formate? We don't have a whiteboard, right? This is much easier to do with a whiteboard. So the answer is if you actually look at how you calculate an Osm gap, so a calculated Osm is, you guys remember? It's 2 times sodium times glucose over 18. You guys do it differently, I don't know. I'm not gonna do the Canadian version. But it's, the important part of the actual calculation is 2 times sodium. Why is it 2 times sodium? Because it's sodium plus whatever anion sodium's interacting with, right? So as soon as methanol turns into formate, it's now electrochemically active and starts associating with sodium, right? So it actually now takes part in the actual anion gap or the Osm gap calculation and falls out of your Osm gap, right? So if you carry that over, anything that causes an anion gap will not cause an Osm gap, right? And you can look at this in DKA. You get elevated Osm gaps in DKA because of acetone, right? Which is non-electrochemically active. But your other ketones, because they're electrochemically active and cause an anion gap, won't cause an Osm gap. So to answer your actual question, yes, you don't know where you are on the timeline, which is another reason why it's hard to use an Osm gap to diagnose these patients. And if they don't tell you that they have toxic alcohol on board, they're gonna look drunk, right? So usually what happens, they come to the ED, they look drunk, we put them in a corner, and then all of a sudden they start getting sick, and we measure their labs, and they have a whopping anion gap. It's hard. I don't think we have a better answer. We can't go measuring Osm gaps on every alcoholic that comes in and start treating them. We kind of just have to watch them and see what happens. But if you have a story that someone drank a whole bunch of toxic alcohol and then came in, you kind of have to trust them, right? And at that point, you can block them with fomepizole, and they'll never have an anion gap, definitely. And depending whether it's ethanol or ethylene glycol or methanol, it depends on if you have to dialyze it off or not. Methanol has like a half-life of 5 days, so usually you have to dialyze it. Ethylene glycol, your kidneys will excrete eventually.
I'm wondering how accurate capillary ketone measurements are. I don't know if you have any information on that.
I don't. I'm sorry. I don't know.
All right.
Cool. Thank you.